The last integration technique using partial fractions we're going to go over is when you have quadratic factors. Now, when you have a quadratic factor in the denominator, you have to have a linear term in your numerator. That is just how it works. It has to do with when you were to combine it back up, it's possible that a linear factor was there to create the fraction when you put it all together. And so let's break this up and I'll kind of explain that a little bit more in detail. So this fraction must come from a function with x and x squared plus 1 in its denominators. So notice it doesn't have any repeating terms, but in order to get 2x minus 3, a over x is one of my fractions, but my other one, in order to make sure I get the right linear combination for my numerator, needs to have a linear term in the top, okay? And if you had a cubic, you would need a quadratic in the top. It always has to be 1 degree less in your numerator. All right, when I multiply through by that denominator, I end up getting that 2x minus 3 equals a times x squared plus 1, and bx plus c gets multiplied by x. All right, using some strategic substitution, I am going to let x equal 0. That's going to let me solve for a. So I get negative 3 equals a times 1, and so a has to be negative 3. Now that I have a has to be negative 3, I probably need to do like the undetermined coefficients method for the other two, because I'm not seeing any other zeros for this one here. And then same with this here. So I do know that 2x minus 3 needs to be negative 3 times x plus 1 plus bx plus c times x. And let's go ahead and expand that right-hand side. So negative 3x squared minus 3, and then plus bx squared plus cx. Now again, I don't have an x squared term over here, so that means that my two x squared terms over here must cancel each other out to get me no x squared term over here for this to be equal. So if a is negative 3, b must be 3. And then also, if you notice on your x terms, we only have one x term. So c must be 2. All right, so let's go ahead and integrate that now. I'm going to have the integral of negative 3 over x plus 3x plus 2 over x squared plus 1. Sometimes you'll be able to see right away that you do have an antiderivative on the second one with the x squared plus 1 that's in the top. However, if I let that be a u on the bottom and then treat it as a natural log, the derivative is just 3x, not a 3x plus 2. So I have to then split this up into 3x over x squared plus 1 and 2 over x squared plus 1. And that's very common to have to do when we find these integrals. And again, that's the reason why we need to have that bx plus c on the top of the x squared plus 1, is because like that's what's creating that overall fraction. If you were to expand that fraction out as best as you can, okay, or as big as you can, like this would be it. This would be the combination that created the original integrand. All right, my first antiderivative is going to be negative 3 natural log of x. I'm going to let this bottom be u. So that means du equals 2x dx. So this antiderivative must be 3 halves natural log of x squared plus 1. Now over on our other side here, that doesn't have an x at all. We need to know that this is the antiderivative for arctan. So plus 2 arctan of x plus c.